Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 4. Today we are going to talk about the basic materials related to engineering, cover a small topic on structure of materials, also discuss about the material properties as a function of the basic molecular structure. As you know that solids are known for their capability to retain definite shapes, and thus the bonding mechanics between the molecules forming a solid is a very important thing. So we are going to actually cover that aspect in this particular topic. So let us look into the basic theory of the bonding between solids. So let us say you have two atom systems, and these atom systems are sufficiently close to each other and have their outer electrons shared by both the nuclei, which results in an attractive force between the two atoms. The force increases with the decrease in the distance between the two atoms. However, the two atoms do not collapse per se, they remain at a certain equilibrium distance where there is a repulsive force as well, which is generated because of the nuclei coming close to each other, and there is an attractive force between the so called electrons of one and the nuclei of another. And these two attractive and repulsive forces, they are in equilibrium with each other. So that is really the position where the two atoms would come and be stabilized, and we call this equilibrium a stable equilibrium. Okay. So obviously why we call it stable equilibrium is a different issue, that if supposing we were to plot the force, let us say, between the atomic system per unit, the distance between them, and you can see that the attractive force is given by this dotted line right about here, okay, and the repulsive force is given by the solid line, and you can see that beyond the point of equilibrium A, which is corresponding to a distance d between the two atoms, the repulsive force suddenly increases, and the attractive force, the slope at the attractive force may not be that high. Okay. So therefore, if the two atom systems are to be taken closer than the equilibrium distance, the repulsive force would outgrow and they would like to go back. Okay. And similarly, at the other end of the equilibrium, let us say for example, if you cross d and you increase the d, the attractive force becomes relatively larger in comparison to the repulsive force. One of the reasons why this system is really a stable equilibrium. Okay. So the equilibrium interatomic distance d is really that distance where the attractive and repulsive forces are balanced, and you have already seen that this balanced point is really a stable equilibrium point for the two systems when we are talking about bonding of solids. So the mechanism that we talked just earlier is only one reason why the atomic system should bond. There are various possible other interactions which are also known as covalent bonding, where there is a sharing of electrons between the atoms which would make the atomic system stabilize. So in a given solid, one or more bonding mechanisms may be simultaneously also active, and the nature of bonding mechanism depends on the electronic structure of the atoms which are involved. And some mechanisms in solids may be something like, let us say, metallic bonding, van der Waals bonding, so on and so forth. So as we all know that in metallic bonding there is a large number of free electrons which are present, and then there are different atomic centers which are there. Typically they are the nuclei centers, and these atoms, these free electrons, they formulate a common electron cloud, and they move through a bulk orbital, which is also the conduction band of such metals. So the rest of the system consists of positively charged ions. You can see reflected here the metallic bond scheme. So positive charge ions, for example, which are in these places, and then the electrons, a sea of electrons, move around in a common orbital. So this is one way where the metals are normally participating in, metallic atoms are normally participating in bonding, and also because of these electrons, the metals develop something called the luster and shiny surfaces, as we have seen commonly. So Having said that, there are other mechanisms which or other let us say systems like let us say alloys etc., where similar bonding mechanisms would interplay. And the problem is that when the atoms become inert in nature and they have let us say filled up outermost orbitals, then in that case the sharing can really not take place, and this results in something called very weak short range force of attraction, which is also known as the van der Waals bond. The origin of this force is attributed to a rapidly fluctuating dipole moment. I will just show you how these van der Waals bonds would work. So, let us look at the figure right here, which talks about the origin of such bondage. The figure shows two molecules at a distance d and each of which has a symmetric charge distribution. So, let us say there is a tendency of one of these atoms to have negative charge towards one end and positive charge towards the other. So, there is some kind of a symmetricity in the charge distribution. There can be many such forms of symmetricities. For example, this is case 1, this is case 2, this is case 3, where you can see alternate charges or charges of opposite type facing each other, and alternate charges or charges of same type being alternate in alternate flanks between the atoms. So, all the three different overall configurations of charge distributions lead to the development of an attractive force through the individually though individually the molecules are neutral, but then there is some kind of a force which develops between this negative charge center and this positive charge center, for example, or even when we are talking about a crisscross interaction between this center and this center, or this center and this center, so on and so forth. And this continues throughout the crystal, throughout the solid where these atom pairs are available, and you can think of it as if there are different pairs of such atomic systems from one end of the solid to the other. So, obviously, there are going to be some forces because of these charges, and if you look at a single atomic system, it does have something called a dipole moment because of this charge separation. And mind you, these dipole moments are also amenable to variation if you subject such atomic systems to external fields or something, or magnetic fields or something like that. So, there are going to be these dipole formulations in such atomic systems, and what people have observed is that if this is really the cause of the bonding, the force varies inversely to the distance to the power of 4 between such atomic systems, and therefore, this bonding is very weak. As the distance goes slightly away, the reduction of the force is substantial. Okay. And so, therefore, this type of bonding is very weak, and it is active in weak and low melting point materials, and this can be something like let us say paraffin wax or plastics, or these kind of materials where generally you find the melting point to be quite low. And one of the reasons are that vis-a-vis the metallic bonding system, which is much stronger, in this case the bonding forces, they vary as the inversely proportional to the distance to the power of 4. So, a little bit of atomic vibration would lead, which is actually proportional to the amount of thermal energy that you are delivering to the system. It will lead to the separation between the atoms, or enable the atoms to come into a fluidic state or a flow state, and which is the cause of a lower melting point in such materials. So, it is obvious that the strength of the bond controls the properties, for example, melting point of a material. So, that is how the van der Waals system of bonding would work. And typically, when we talk about metallic systems, there are the atoms formulate certain organized patterns, and you can call it that this arrangement of atoms is really a long range order, and such systems are also known as crystals. Okay. So, typically there is a certain arrangement, a basic arrangement, which is the smallest unit, and you can think of it that this unit is assembled spatially with respect to each other, block by block, so that the whole system comes up. So, there is some kind of a repetition of the arrangement of that one unit as far as the whole solid system is concerned, which is being composed of these small unit cells. So, these systems are known as crystals, and the property of a material, it very heavily depends obviously on the bond strength, but also on the arrangement of the atoms in such crystal lattice. And if you have an arrangement which is very well ordered, well structured, then obviously the strength of that system would be much higher in comparison to materials where such arrangement does not exist. Okay. So, such solids are commonly called as crystalline solids, and a large number of situations the whole solid is seldom composed of one single crystal. Instead, it has a large number of small randomly oriented crystalline grains from the whole solid. You can see such a composition here, that this one grain, or for example this one grain, they are having a long range order of arrangement. The crystal structure is repeating, as you can see here, or as you can see here, but then the structure does not repeat beyond these boundaries, which are also known as the grain boundaries, and such systems are typically known as polycrystalline systems of arrangements. So, our learning experience is so far that we have learned what kind of bonding systems work between different atoms, so that there can be strength incorporated, about the arrangement systems which would be there over a longer range or a shorter range, which would enable structure to be called crystalline as opposed to non-crystalline or polycrystalline. And so, the next topic would be that what are those small blocks which actually compose of this crystalline structure. And so, the three commonly observed crystal structures in terms of those small units, also called unit cells or blocks, are the body centered cubic structure, the face centered cubic structure, and the close packed hexagonal CPH structure, out of which the FCC and the CPH have the most dense amount of packing that is imaginable. So, the interatomic distance in such crystals is actually of the order of 10 to the power of -7 millimeters, or about an Armstrong unit. And typically when the material solidifies, particularly in case of metals where there is a possibility of the crystal growth, the route that is taken is that you start with the liquid metal, and then after solidification, the solidification centers are well arranged. The centers in terms of unit cells, which have a dimension of about an Armstrong, 0.1 nanometers, and there can be several such arrangements: body centered cubic, face centered cubic, hexagonal, close packed, or then there are crystal structures which can change as a function of temperature, called allotropes, so on and so forth. You then formulate the repetition of these unit cells, which leads to the long range order of arrangement of materials called crystals. So, you have now in these crystals lattice imperfections, dislocations, so on and so forth, and these crystals either would be formulating single crystals or polycrystals. Single crystals, of course, are used for very specific applications where you really need a defect free predictable behavior of the material. One aspect that is very different, which happens very differently in case of some materials, is that the predictability of the material behavior may not be that certain. So, polycrystalline materials are supposed to not be completely predictable in terms of their mechanical behavior, but at least single crystalline materials are used in solid state devices, for example, where you need to predictively ascertain the electronic property of the material, or for turbine blades where things like mechanical strengths and compressibility or load bearing nature of the materials are very important. And so, there typically tend to use the single crystalline material. So, the polycrystalline materials on the other hand can be used for regular applications where the predictability of the strength may not be of that big of a concern. For example, you can use them in paper clips, bolts, springs, wherever you are deforming the material to use it post deformed state, like I beams, aircraft fuselage, so on and so forth. The grain boundaries in such polycrystals are very important. The concepts of plastic deformation and anisotropy are very important in recording such polycrystals, and we are going to look into some of these aspects as we go along. So, let us look at the three different crystal structures which we have talked about. The first one is a body centered cubic structure, and what you can see here is that there is a central atom which is placed at the center of the cube, and there are contributions of 1/8 of the atom coming from all different edges of the cube. Okay. So, that is how you are able to make a unit cell, something which can be more clearly illustrated by a wire diagram like this. So, obviously, this particular section is an eighth of the the total sphere, and so 8 such small contributions together would formulate one atomic unit. So, there are 3 different structures. In fact, one is called the hardball model, which is represented here. This is the unit cell model, and then it is a single crystal with many such unit cells. So, you can think of the packing or the arrangement. So, one of these cubes is what we are referring to here as a unit cell, and you are repeating them 3 dimensionally in space for you to be able to envision how this system looks like. So, obviously, geometrically, if we want to find out the diameter of or the radius of the atom, we need to get this number, the interatomic spacing or the size of the unit cell, which can come from Bragg's diffraction or some other experiment, and you can actually be able to now predict the atomic diameter based on the lattice distance, which can be recorded by experiments like Bragg's diffraction. So, let us look at what is the geometric relationship available between the radius and this lattice distance. So, basically, if I just look at diagonally what is going to happen here, for example, you have radius r, radius 2r and radius r combined together. So, you have in total 4r, and this results in the diagonal distance in the unit cell, which is actually equal to a cube a square plus a square plus a square whole under the root. So, typically that is how you represent the diagonal distance of a cube of length a, and so you have a root 3 equals 4r, or in other words the radius r can be represented as a root 3 by 4. So, if you have this from an experimental evidence, this is also the lattice constant which would come up in a Bragg's diffraction plot or something. You can easily calculate what is the radius of such a atomic system which formulates this body centered cubic structure. So, we will also similarly discuss the face centered cubic and the closed packed hexagonal structures in the next module. So, this module is closed here. Thank you.